Hello everyone, my name is Xiatao Sun. In this video, I will present our works on imitation learning for autonomous racing. To begin with, I will first present about our comparative study on various imitation learning algorithms for autonomous racing scenario. Recently, autonomous racing becomes more and more popular thanks to the development of autonomous driving techniques that keep pushing the limit of vehicles and the development of reduced-scale racing platform. Most existing approaches in the autonomous racing community use human-engineered method or reinforcement learning. Since usually imitation learning is considered as an alternative or a bootstrapping method for reinforcement learning, we are curious to see how various well-known imitation learning methods, including behavior cloning, data aggregation, human-gated data aggregation, and expert intervention learning, to see how they perform in the context of autonomous racing. We open-sourced all the code of this project to help anyone interested in applying and developing imitation learning methods for autonomous racing, which can be found by scanning the QR code or enter the link on the bottom of the slide. Here is a short demo video showing a F1Tenth car controlled by policy learned from imitation learning, driving in real-world scenarios. The trajectory is a little bit wobbly, which might due to some symmetrical gap in friction, dynamics, etc., as the policy is purely trained in simulation. But as you can see, overall, the policy has decently good performance, and the vehicle can complete one lap when controlled by this policy. So, after this demo video, I will talk about our implementation in details. To learn the end-to-end control policy using imitation learning and compare various learning methods fairly, we use a pure pursuit algorithm as the expert, which takes a ground truth position and orientation as the input, and alters the steering angle and speed correspondingly. The learn policy, on the other hand, can only get the LiDAR observation. It is essentially a two-layer perceptron with 256 hidden units. The output is the same as the expert, which is the steering angle and speed, so it's an end-to-end policy. Then, we have our imitation learning algorithms to feed the learn policy with data from the expert. Since using imitation learning to bootstrap reinforcement learning is also a common practice when applying imitation learning, we also develop pipeline for bootstrapping learn using proximal policy optimization to compare the efficiency of bootstrapping, which I will talk about in details in upcoming slides. Finally, all policies are trained in the F1Tenth streaming environment without domain randomization, which is either deployed to control the actual F1Tenth vehicle in real world or in simulator for testing and comparison. After talking about the implementation, I will now move on to our comparison results and metrics that we use to evaluate each method. Briefly speaking, our testing can be put into three categories, which are training efficiency, performance and generalizability, simulation test, and real-world test. We compare the training sample efficiency of each method in the simulation with respect to three different experts with different average speed. As you can see from the plot on the right side of the slide, all methods can converge to a decent policy when the speed is low, except for BC, which is behavior cloning. It is the most rudimentary imitation learning algorithm that suffers from error accumulation. When the speed is normal, only the method that has interactive mechanism, which are AG-Dagger, that is human-gated data aggregation, and EIL, that is expert intervention learning, only the two methods converge to a decent policy. The interaction mechanism is basically if the expert senses that the agent is not behaving correctly, it just directly takes over the control and provide demonstration data for the agent. And overall, we can see that imitation learning methods with interaction mechanism tend to have better sample efficiency. And as I said in previous slide, imitation learning can also be used to bootstrap reinforcement learning to help alleviate the sparse reward problem in reinforcement learning. Because of that, we also test the bootstrapping efficiency of these imitation learning methods with PPO. The results show that when combining with imitation learning, the performance of PPO policy gets improved more or less, and when using interactive methods, the improvement is extremely noticeable, which can also help validate the point that interactive imitation learning tends to have better sample efficiency. After training the policy, we then test their racing performance in the training map. Overall, Dagger, AG Dagger, and ELL, they all incorporate the idea of data aggregation, that is, including more diverse state action pairs into the training data. It helps mitigate the problem of compounding errors, which can be shown by the table at the bottom of the slide. As you can see, they usually can complete one lap when the speed is slow or normal, but when the speed is fast, only ELL can successfully complete one lap. So besides performance, generalizability is also an important factor to take into consideration when using learning-based approach. The problem with imitation learning is that since the learner is highly relied on the state action data provided by the expert, it is typically hard to generalize to on-scene environment, which is also reflected by the table on the slide. You can see that all imitation methods fail to generalize to an on-scene environment, but when combining with PPO, all of them suddenly have great performance. Note that when training PPO directly, the performance is also extremely limited because the agent at the beginning phase of training tend to perform a lot of random work in order to get a good understanding of state transition and rewards. By using imitation learning, we can greatly reduce the amount of time for exploration in the beginning. And by using bilateral distance to calculate the state action distribution between learn policy and the expert, we can notice that interactive imitation learning can learn policy that behave more similar to the expert. Lastly, we tested the learn policy with domain randomization in real world. You can see that the policy learned using interactive imitation learning can traverse further distance compared with non-interactive approach like BC and Dagger. The combination of AG Dagger and PPO yield the best performance, but you can see that when incorporating PPO, the trajectory becomes more wobbly. This might be because of the reward function, which defined as a term for staying at the center line, but actually the expert is not always seeking to stay at the center line. So in conclusion, the key takeaway of this benchmark comparison are listed on the slide. Imitation learning algorithm can train or bootstrap high-performance policies for autonomous racing. Interactive mechanism improves sample efficiency and bootstrapping efficiency of imitation learning. And combining imitation learning and reinforcement learning can achieve fast convergence and better generalizability. Now, after going through the benchmark comparison, let's look into MegaDagger. In this work, we propose MegaDagger, an imitation learning method for learning from multiple imperfect experts. Existing interactive imitation learning algorithms assume having the access to a single optimal expert, whereas in real-world scenarios, we usually only have access to multiple imperfect experts. For example, in the autonomous racing scenario, we usually can only have multiple experts that cannot provide perfect demonstration at every round. During the learning process, we may want to collect demonstration data from all of them and learn a cumulative policy that takes the advantages on every expert. In order to effectively apply interactive imitation learning in such scenarios, we need to address the challenges of undesired and conflicted demonstrations. Here is a comparison between our proposed MegaDagger and HEDagger, a well-known interactive learning algorithm. By comparison, the racing policy learned using MegaDagger with 5 imperfect experts can overtake in scenario that policy learned using HEDagger fails to overtake. The learn policy with MegaDagger can also outperform the expert, As demonstrated by the video on the slide, because McDagger learns a cumulative policy by strategically selecting the goal state action pairs from different experts, it is able to outperform the expert. Here is a McDagger algorithm. The algorithm starts with an empty global dataset and a randomly initialized novice policy. It iteratively incorporates demonstrations from each expert into the global dataset and train a new novice policy using the updated dataset. The core part algorithm are the data filter and the conflict resolution function. As seen in the slide, both HDagger and McDagger incorporate the gating function to allow the expert take over the control and provide demonstration. When comparing to HDagger, the improvement that McDagger add to the learning loop and training pipeline is mostly the data filter and conflict resolution in order to cope with the incorporation of multiple imperfect experts, as labeled in the orange box on the slide. We will first talk about the data filter. Let's still take autonomous racing as an example. When the vehicle collides with obstacle during the demonstration process, we will want to remove this undesired step, along with some previous steps that bring the vehicle to such undesired state. To mitigate the challenge of undesired demonstrations, we design a data filter that can strategically terminate the rollout and truncate undesired demonstrations. The data filter is based on the control barrier function. The safety score is calculated by the subtraction between the CBF values of two consecutive time steps. If the safety score becomes negative, the current rollout will be terminated, and a fixed number of demonstrations will be truncated at the end of the dataset. Before performing the actual evaluation, we first perform some preliminary experiments to find out the most suitable beta, which is the truncation steps for our scenario. So we first change the beta parameter and see how it affects the performance of our method. As the image on the right side of the slide shows, we show how the number of truncated steps, which is beta, affect the performance of the policy in terms of overtake rate and collision rate. For the truncation step, we empirically find that when beta equals to 70, both overtake rate and collision rate works the best. After setting up the parameter, we evaluate the effectiveness of our proposed data filter using lane switchers with different undesired behavior probabilities as expert. The lane switcher is an algorithmic oracle that has access to the transformation and state of both the ego vehicle, the opponent, and the track. So it is able to plan perfect trajectory for the ego vehicle. To incorporate undesired behavior into the analysis, we introduce PU, which is a chance of undesired behavior to happen. When the undesired behavior happens, we reverse the steering angle from the oracle and speed up the vehicle to make it easier to collide. On the right side of the slide, the green bar represents policy with the data filter applied, and the right bar represents policy with random truncation of the same number of steps. We show that using the data filter demonstrates noticeable improvement over random data truncation, both in terms of overtake rate and collision rate. After going through the data filter, let's talk about the second part of the algorithm, which is the conflict resolution function. To resolve conflict, we propose a function for checking similar observations and scoring the action associated with these observations. We first determine similar observations by calculating cosine similarities using matrix manipulation in one batch with respect to similarity threshold. Then, for our context of autonomous racing, we use a linear combination of safety score and ego velocity after min-max scaling normalization as indication of safety and progress respectively to choose a best action and overwrite all other actions with similar observations. As for the cosine similarity threshold, We performed hundreds of rollouts while changing the cosine similarity threshold and find that when setting the cosine similarity to 0.95, it works the best for our scenario. The left side surface plot indicates the connection among the cosine similarity threshold, number of rollouts, and the collision rate, whereas the right side indicates the connection among the cosine similarity threshold, number of rollouts, and the overtake rate. As the red circle in the plot indicate, when cosine similarity is set to 0.95, the policy reached to the peak performance. We should roughly evaluate and compare MegaDagger with HEDagger in the context of autonomous racing. When compare MegaDagger, HEDagger with a data filter, and HEDagger without the data filter on different maps, we show that policy learned using MegaDagger can outperform policy learned using HEDagger in terms of both overtake rate and collision avoidance on various different maps consistently. We also evaluate and compare the policies learned using MegaDagger with the expert. As the table and graph indicate, the learned policy is able to outperform all experts by leveraging the complementarily goal demonstrations. As the collision plot visualization indicate, the collision from different experts forms a complementary distribution. By using the data filter and conflict resolution function, we can aggregate goal demonstrations from all experts together and ultimately learn a policy that is able to outperform all imperfect experts. We also deploy the learn policy onto a real vehicle and show that the learn policy is able to safely perform overtaking when racing with an opponent vehicle. The video on the slide shows the policy deployed on the physical vehicle with the opponent being pure pursuit algorithm. And as the video illustrated, the ego vehicle is able to overtake the opponent multiple times effectively and safely. We open source the code to facilitate further research and contribute to the community. The code can be found by scanning the QR code or accessing the hyperlink on the slide. Thank you for listening.